Welcome back to this series on support vector machines and credit modelling. We are deep in the weeds of work on the kernel trick and trying to understand what that does. And last time what we talked about was just explaining what the kernel trick is, how it works, and how it works in particular with the quadratic kernel, which is a really useful kernel for explaining how things work, but not a particularly useful kernel if you're looking at credit modelling. So we'll just finish off some of the stuff on the quadratic kernel and polynomial kernels more generally, and then we'll move on to kernels which are a bit more useful for credit modelling. So last time we finished off by looking at the results of a quadratic kernel, which shows you that it is giving you a best separating ellipse between data which is close to the centre and data which is not close to the centre. Now, the kernel which we use is actually described as a homogeneous quadratic kernel. A more general form of that kernel has a constant in it, so it becomes xm transpose xn plus c all squared, with c in this place not being a Lagrangian but just being a constant which is greater than or equal to 0. And what it essentially does is it determines the relative importance of the higher and lower powered terms in that kernel. So if we're trying to find out what phi is, what the transform is for this expression, so what it represents in input space, we need to expand this expression. Now the first stage of this expansion is fairly straightforward. It's xm transpose xn all squared plus 2c xm transpose xn plus c squared. So just a straightforward quadratic. But then we need to do some further expansion for the first couple of measures that we've got there. So let's take the first couple of parts of that expression and treat them individually. So xm transpose xn all squared is x1m x1n plus x2m x2n all squared, which gives us something which we've seen before, x1m x1n both squared plus x2m x2n all both squared plus 2x1m x1n x2m x2n. Then the next piece we're looking at is 2c xm transpose xn, which is 2c x1m x1n plus 2c x2m x2n. And then if we stick in the c squared again, it gives us this much longer expression for the kernel function k xm xn. Now, because k xm xn is equal to phi xm transpose phi xn, that phi being that transform function, what this implies is that phi of xm, the original mapping function, is x1m squared x2m squared root 2 x1m x2m, which we had before, but then also root 2c x1m root 2c x2m and c transpose. So you've got quite a few terms in there. And as you can see, that c is going to be something which determines the relative importance of the x1m and x2m terms and their squared and cross products. So it gives you a few more degrees of freedom to play with there. Now that's what it looks like if you've got just two measures, so EBIT over assets and log of assets over liabilities. But you might actually have a whole range of different measures that you're looking at when you're trying to credit rate a firm. So rather than just being 2 dimensions, it might be 3 or n dimensions, and you're looking at separating planes, separating hyperplanes, and so on. So this is the multinomial formula, which gives you the value of each of the powers that you might have in a multinomial expansion if you've got g measures. And the summation gives you the coefficient for each term which is described by the product. So you've got g measures and you've got the kernel described in this way. What you've actually got is this summation over all g of xgm xgn plus c, so for firms m and n, which can be expanded out into this polynomial, which itself then gets squared, and then you end up with the sum over all g of xgm squared xgn squared plus 2 times this double summation of xgm xhm xgn xhn plus 2c times this further summation over g plus c squared. So it's getting pretty complicated. So this implies that 5xm is equal to this long transpose vector here, x1m squared, x2m squared, then all the rest up to xgm squared, root 2 x1m, x2m, all the way up to root 2 x1m, xgm, then from root 2 xg minus 1m, xgm, all the way up to including root 2c x1m, all the way up to root 2c xgm, then c transpose. So you end up with a pretty hefty vector there. So it's fairly clear why, if you're working in a fairly large number of dimensions, why you really wouldn't want to have to work in that input space, why it'd be far nicer to move to a kernel like the one described. And you can even move to from quadratics to higher powers, so use d rather than 2. You can add a scaling parameter a, so the most general of these polynomial kernels becomes xm transpose xn over a plus c all raised to the power of d. And the expansion here, you can imagine how complex that becomes, and how complex it will be to take that back to input space and look at what the transform is. But the kernel trick means you don't actually need to do that expansion. That's one of the beauties of the kernel trick. Now, the linear function is trivial. The polynomial kernel is really not very well suited to credit risk. But what's called the radial basis function, the RBF kernel, is much better, and it's got some very interesting properties. So this is the one which you're most likely to use when you're looking at credit risk modelling. So the starting point for the RBF kernel is the Gaussian kernel. And the kernel function here is e to the minus xm minus xn transpose xm minus xn all over 2 sigma squared. The sigma kind of represents here the variance between the observations. So although it's kind of trivial because we're not going to be using the Gaussian kernel itself, but that's kind of what it represents. Now, it is worth noting that that term, the xm minus xn transpose xm minus xn, because what that is, that's the Euclidean distance between xm and xn, which does suggest some similarities with the KNN approach, and there are some Mahalanobis distance-based versions of this. That's getting a little bit too complex for what I'm going to be covering, but it's worth just recognising that similarity and potential transferability between this approach and the k-nearest neighbour approach that we talked about some time ago. So the parameter sigma, if you're looking at it from a Gaussian point of view, it is the spread parameter calculated from the data, but it's more often just used as a variable which you use to calibrate your kernel to the data. And often a substitution of gamma, which is equal to 1 over 2 sigma squared, is used. So the end result is that the RBF kernel is e to the minus gamma xm minus xn transpose xm minus xn, and gamma is something which you tweak to try to get the best fit to the training data that you possibly can. So let's have a look at the RBF kernel and just see why it is interesting. You can expand that function there as follows. So it becomes e to the minus gamma xm transpose xm times e to the minus gamma xn transpose xn times e to the 2 gamma xm transpose xn. And it's that final term which is interesting, because e to the 2 gamma xm transpose xn can also be written as an infinite expansion. And if you have this infinite expansion, it becomes 1 plus 2 gamma xm transpose xn plus 2 gamma squared over 2 factorial xm transpose xm squared plus 2 gamma cubed over 3 factorial xm transpose xn cubed, and so on. So this infinite summation below. So it should become clear that if you've got this infinite summation, what that means is there's a bit like a version of a polynomial kernel with infinite powers, which is quite interesting and quite useful, mainly because the kernel itself is much more straightforward. So if you recombine that, this is what you get for this kernel function: e to the minus gamma xm transpose xm, e to the minus gamma xn transpose xn, times this infinite series, 1 plus 2 gamma xm transpose xn, and so on. And if you've got g measures that you're looking at, then you get xm transpose xn is equal to the sum over all g, xg, xm, xg, xn. Xm transpose xn squared becomes the sum over all g xgm, xgn all squared, which is equal to that summation, and so on. And in terms of the multinomial theorem. So what that implies is that the mapping function that you've got there is equal to e to the minus gamma xm transpose xm times this infinite series. In other words, a vector of infinite length including all of the powers of the elements of xm and all of its cross products with the relative weights controlled by this parameter gamma. So that's pretty powerful. So the larger gamma is, the more important the higher powers become. So if you've got very small gamma, it means the kernel trends towards a linear kernel. If you've got a very large gamma, it means the kernel becomes like a high order polynomial. And you find gamma using something called cross-validation. So we look at cross-validation, and cross-validation itself is it's a pretty large subject. There's a number of different approaches that you can use, but the broad approach is you split the data into training and test data. You fit the model to the training data set using different values of gamma, and you see how each of these fits performs on the test data set. And then you repeat this on various different splits of the data into different training and test splits. And the optimal value of gamma is the one that correctly classifies the highest proportion of the test data set. Now, you can also use this to try to find the optimal value of C in a soft margin support vector machine. As I say, there's a number of different approaches you can use for cross-validation, but it does just reinforce that when you're looking not just at what your parameter gamma should be, but also how soft the soft margin should be, because the chances of you getting a hard margin SVM with real-life data is pretty slim. So you want to try and find the best parameter you can for your soft margin SVM. It just does reinforce that these are both just parameters rather than things which are cast in stone from the start. So gamma is really not going to be driven by the volatility of the variables that you're looking at. It might have a relationship to sigma in theory, but it doesn't in practice. Just quickly, one other kernel worth looking at is something called the sigmoid kernel. So it has an S-shaped form. This has the following formulation, which is the hyperbolic tangent of gamma xm transpose xn plus c. Now, this isn't so much used in credit risk modeling, it's more used in neural networks, but you can do an expansion of the hyperbolic tangent function, and it shows similarities with the RBF kernel. I mean, the Taylor expansion is pretty messy. It's the sum over from k equals 1 to infinity of 2 to the 2k times 2 to the 2k minus 1 times b2k x to the 2k minus 1 over 2k factorial. And b2k is the Bernoulli number for 2k. Look it up. It is not intuitive at all, but it is a thing. More instructive is perhaps to just look at what the first few terms of the kernel are if you do expand them. And what you get is gamma xm transpose xn plus c minus gamma xn transpose xn plus c cubed over 3 plus gamma xm transpose xn plus c to the 5 over 15 and so on. And if you've got g measures there, so xm has g elements in it, then you can use the multinomial theorem within that to work out what this looks like in terms of a transform function, and what it will tell you is that 5xm is a vector of infinite length, including, in this case, all the odd powers of the elements of xm and the cross products, with the relative weights again controlled by gamma. So similar in some ways to the RBF kernel, in that you're taking something which looks a little bit interesting, but the reason it works is because it can be restated as a polynomial form, but the kernel itself is far more compact and easy to calculate than that. So there we go, a little bit more on some more useful kernels and why you'll often see the RBF kernel used in credit risk modelling. And what we'll do next time is we'll just look at how you can use the RBF kernel in practice in R and show you how straightforward it is to get some real life results using this kernel.